Alright, so welcome back to the final video of this playlist here. And we'll do a little reminder of what we're about to do here. So, in the previous videos, I talked about how our graph for this of the SRK EOS here is not exactly correct. It doesn't match the one that we have made experimentally, right? Uh, we have, we don't have the two-phase envelope that the experimental one has right here. That connects the liquid and vapor phase, right? With the liquid and vapor phase volumes via this very specific pressure, right? This constant vapor pressure. And we don't have that. And so we were talking about how we could, how do we make that two-phase envelope on what we have here? And well, that process is called the Maxwell construction, right? And so we were going along talking about how the area of the curve here along this specific pressure, these two areas have to be equal in order for that, specific pressure to lie on that two-phase envelope curve. Um, and so we were talking about how this is a cubic EOS here, right, for a specific isotherm. And we were talking about how we needed to find, well, the three specific roots along this specific pressure, right? And well, how would we find those three specific roots? And well, we used a method that we discussed last video called Cardano's formula, which was pretty straightforward. And now we, in our Python here, have the means to find those three roots. Now all we have left is to, well, find these areas firstly, right? And then set them equal using some method. I will be using uh, SciPy root, um, sort of changing it a little bit to fit what we need for this. And then obviously, lastly, uh, graphing that two-phase envelope onto our graph. So that was just a bit of an outline of what we're going to be doing. So let's get started with the first step, right? Finding the areas. So let's go to the Python code. All right, so let's get started on finding the areas here. So, um, in terms of integration, we have two methods we could use, right? We could do analytical or numerical. Um, in my case here, I will be using numerical integration, only because we are doing this via code, right? We're coding this out. So, the specific method that we'll be using is Gaussian quadrature. And well, this method has a reputation for being very accurate, coupled with the fact that we're doing it via code. So a computer is doing all this, right? Um, its accuracy compared to an analytical method, it, it's comparable, right? We won't have to worry about a value being that far off, if at all. Maybe 10 decimal places to the right, there might be a different value, but at that point, it won't matter, right? So uh, I need to import it. So I will do that from scipy dot integrate import quad. Right. So we can get started. I'll get rid of the test here, and we can get started on this. So let's make a function to find our areas. So I will name it, I guess, cubic areas. Right. And so what values will we need to supply this function for it to work, right? Well, uh, this is a specific isotherm, right? So we need temperature. Another obvious one, right, is the EOS. What EOS do we want? Well, we'll default to SRK, and if I ever want to come back, I can create one for van der Waals. And then a specific pressure guess, right? The vapor pressure. That we need to actually integrate the area, right, between difference between the two, right? So we need the pressure as well. All right. And so quadrature, the Python one at least, it needs some specific things. It needs a function to pass through it so that I can actually integrate. It needs a function to integrate. And as what we have right now, we don't have a function to integrate, so we have to make one. So we'll make one inside this function itself. So call it integrand. And for now, we'll just put that as v. And what will return? Well, what are we integrating? Well, we're integrating the area below the pressure minus the area below this curve, right? To get this. Simple uh, integral stuff. So, well, what is the cubic EOS, right? And well, we have that up here. It's this, right? So we can, uh, I'll just type it, cubic underscore P, and well, we need V, T, and EOS is the EOS, right? Oops, if I type it right. All right. Sorry, hit the mic. Now we need like I said, the limits of integration, right? So, well, we got those from last video. So V1, I'll unpack it too here in the same step. V3 equals, well, cubic underscore V, pressure, temperature, and EOS. All right, well, let's do the integration. All right, so quad needs the, well, function to integrate, right? That's our integrand. And now it needs our limits. So we have V1 to V2 for this first one, right? And another thing about quadrature, it actually returns two things. It returns the actual area that we need, and then it also returns a second value, which is the error approximation. And well, we can't do anything with that error approximation, right? Except for maybe see how close it is, see how accurate it is. Well, we already know it's accurate, so who cares, right? So we only want the first value, so we'll pull that out in the same step here. And well, it's the same thing for the other area. So into can't type, very can't type. All right, and it'll go from that to that. And once again, pull out the first value. And voila, we have our areas. So, um, what do we do next? Well, it would be a good idea to test it out. Cubic underscore areas, right? 91K, 373.15. And yeah, it's working. All right, these are my test values from before, so and they match up. I can't tell for sure if they exactly match up, but they look about right. So at least we know this function is working, right? I don't want to mess up like I did in my previous videos. So right, what's the next step now? now that we have this working function for the areas, well, we want to set them equal, right? And the only way we can gauge how close we are to setting them equal with whatever pressure we put in is to find the difference of the two, right? So let's make a function for that. So we'll call it just areas difference, right? Areas difference. And so we got to do a little bit of thinking ahead. Um, we know this function here will be used to gauge how close we are to setting them equal. And like I said earlier, we'll be using a root solver to actually lead it to 0 to make them equal. And we have to think about the root solver here for a second. So the root solver only takes inputs of arrays. And so the function has to have an input of array. And the root solver also then outputs an array. So because of that, we have to make our pressure input that we'd usually have as just a singular value an array. Technically, just in name though. You'll see in a second here. So we'll also need the temperature, right? Because we'll be using the cubic areas function that we've created, right? And why I say only a name? Well, pressure is going to be the only value in that array when we pull it out. So yeah, that's what we have to do for it to actually work for a root solver. And so what names could we give the areas, right? Left and right, because, well, one's on the left and one's on the right, right? And now we can use our cubic areas and assign them names. And a EOS. And return the difference. And as we saw earlier in our test values that are still on the screen here, I just pointed at my screen like you guys can see what I'm pointing at. Anyway, the left-hand side is positive and the right-hand side here is negative. So to gauge how close they are, we would add the two to see how close we are to 0. Right, and well, let's test it out, right? Areas, diff. Uh, we'll put in 91K and the same. My bad. I literally explained that it needed to be an array, and I didn't even put it in an array. Passed right through my shallow brain. Anyway, all right. So what we have as a guess here is 91K. It's all right of a guess. It's pretty close to 0, right? Well, at least we know it's working. So the only thing left to do now is to actually apply it with a root solver, right? So let's do that. All right. So let's start it using the root function, right, to find the correct vapor pressure that links the liquid specific volume and the vapor specific volume, right, the gas. All right, so let's use root, and remember, it needs a function, our function, right? It'll be our areas diff one. Our guess needs to be an array, so I'll do 91,000. And then you also notice that the function that we are specifically using has these two other arguments inside, right? And well, those need to stay constant. And to do that, we will label them as arguments, or args as the syntax. And so since I'm doing this as a one-off, I actually do need to supply the temperature. And I'll do SRK in here. All right, and it works. And this is the true vapor pressure. And so we only need the X portion of this, right? And since this is the true vapor pressure that correctly links the specific volume of the liquid and the specific volume of the gas, well, we should assign it to that vapor, to the variable vapor pressure, right? And so, as you notice, it's in our array right now, and it's the same uh, scenario as what we had before in the areas difference function that we had. It's just one value, and we can pull that one value out using this exact method here. And doing so, I'll show you, pulls out that value, and now we can actually assign it to our correct vapor pressure. And now we have a point on that two-phase envelope that we can plot down now. And so we need to do it with all the other isotherms, right? So we can actually plot the two-phase envelope. And so I am going to intentionally do it wrong so that I can demonstrate all the reasoning behind the final solution of it, right? So, like I said earlier, we need to iterate through a bunch of temperatures. So let's do it linearly spaced. We'll start at 275 and go up to about 610 points. All right. And since I'm actually using variable, I can actually supply t. And we also need our specific volumes, right? Because otherwise, how else would you be able to plot it? So liquid, intermediary does not exist, literally. So we can just give it a trash variable name, and then the gas. And we'll unpack it from cubic V, and using now the correct vapor pressure that connects the two, and the given temperature. And well, as it's looping through, right, we don't want to lose these values. So how would we keep them? Using a list, right? The easiest way to store values. So let's create lists for all of this. Man, my typing is not on it today. All right, and I obviously didn't need this much space between the two. All right, and so every time it runs through, let's add the value that it gets to the list. Uh, and I forgot to put the in, and forgot the colon. All right, and we get an error. And do not worry, like I said, intentional. Not the in and missing colon though. That was on accident. Anyway, we have a constant guess of 91,000 every time we run through. That doesn't make sense when you look at the graph, right? So let's look at this graph. We are saying, well, I guess I don't need to zoom in at all for this explanation. Let's say we are looking at the 600 here, right? And we guessed 91,000. Well, how is that guess anywhere near this supposed value of 19 million? Right? It makes no sense. No wonder why the root couldn't converge, right? Which is the problem here. And so we need to have our guesses changing every time. How do we do that? Well, we can update our guess within the loop, right? So we just need to have it as a variable. So we have it starting at 275. So we can honestly have a pretty low pressure guess for that, and it'll work. But if we're getting the correct pressure every time, that should be a pretty good guess for the next isotherm, right? Because it will be near the vicinity of it. And so we'll do exactly that. We'll replace our guess with the previous pressure. And we can see that it works now. So let's try plotting it, right? And so I will copy this down.
and substitute this as a second figure. All right. So let's get to plotting. Fig2 dot add underscore scatter. Our x will be liquid list. Y's will be the vapor pressure list. And we'll do mode equals markers. And it's the exact same setup for the gas one, except this is a G. All right. And damn, looks like poop. Anyway, let's change our x-axis a bit so that we can get a better look at this, right? So range equals, let's not have this missing, this is empty section here. Let's actually start at where points actually start showing up, right? So we want to use the minimum volume. And we got to remember that this is on a logarithmic scale, so we have to do np.log10 of the value, the minimum value of volume. And let's go to the hundreds and parentheses. All right, this looks a lot better to look at. And obviously see our mistake with our second phase envelope. We have this huge missing section in the middle where there are 0 points. Well, let's do some trial and error stuff here, just to make it look better, right? Well, what if we increase the amount of points? This will take a bit longer here. We run this, and we still have this giant gaping hole between the 2 points. Well, let's increase our temperature. Maybe 650. Oh no, we've got an error. And that error is because, well, we've probably hit the critical point or got too close to it. As you know, on the critical point, there's only one root, and thus we wouldn't be able to unpack 2 roots from it. So we've gotten too close. And well, that continues to be an issue no matter what we do here with this lens space. So for now, let's focus on at least getting these two connected. So how do we do that? Well, we know first off that the volumes, right, will continue on as an x-axis, right? We know that the liquids go from left to right, so that'll start from the smallest to biggest, right? So I'll do a V plot here. So we know we can add the two values so that we can get a continuous x-axis. Plotting points. And well, we would add the gas specific volumes to it too. But we gotta notice that when we calculated these, right, the specific pressure, when it was low first, right, we can use this same exact graph here. It starts here, and that corresponding gas volume is all the way over here, right? So it's sort of coming in from the right towards the left. And well, what do we do about that? That's not reading from left to right, you know, how the graph generates these points. And so we have to do some list manipulation so that's in the correct order. And that's pretty simple. We start at the default start, end at the default start, but go in reverse order. We take steps in reverse order. And well, we have to have the corresponding pressures to those, right? And well, we do the same exact thing. But obviously the values just repeat themselves for this in this case. So we don't have to add two separate lists to each other. All right, and now I will change this back to 600 so we can actually go through. And now we can condense this to 1. All right. We knew that was going to happen, so we need to connect the two now, so we can actually use lines. And what it tries to do is create a giant, it just connects the missing portion with a straight horizontal line. And we know that isn't correct because we have this nice smooth envelope. So that's what we're aiming for. So what I was doing earlier, got reworking the temperature around, right? You notice that values that got super close to the critical point were working, right? But as soon as you got too close, it wouldn't work anymore. And that's sort of like a limit, right? It's a limit. And so we got to try to get as close as possible to that limit. So how can we change temperature to that sort of methodology, right? That thinking. How can we get temperature as closest to the critical temperature as possible? And one way comes into mind is to have T depend on something else, have a function of T. Have T be a function of something else, right? And so now we can start thinking of functions that sort of naturally, that function itself, by itself, gets really close to some limit value, right? And when you think about it, one does come to mind. And that, draw it on here, is the exponential function, right? E to the x. Well, just by itself, it doesn't look correct, right? That's 1. It goes to infinity. It's not really approaching some limits. But, well, what if we, flipped it on the y-axis? What would it look like then? I will erase this. All right, we're doing some manipulation now with functions. If we did that, flip the y-axis, so it'd go well, this way, right? Instead of going this way. And well, I don't want to really draw that. And so what then now is, well, if it's going this way, right? I guess I could have drawn it this way, right? Let's flip it over, right? So right now it's this. We flipped over the y-axis, and now we flip it over the x-axis with that negative, and we sort of get this. And this is starting at -1. I know this doesn't look right, but bear with it. I'll erase it. Right. And that sort of looks more correct, right? It's going towards a limit of 0. And, well, we don't really want that, right? So how about we shift it up 1? And, well, it becomes a function that approaches 1. And, well, we can work with that because we can scale it correctly when it's +1 like this, right? And also, well, we can't have any of it being negative. And so, what do we do now? We have a function that looks like temperature can depend on. That will sort of get it super close to the critical temperature. But just by itself won't work. we need to scale it to what we have on our graph. And that is these insanely high values, right? So we need to get it super close to the critical temperature. And the lowest temperature will be, we'll say 275. So we multiply that to scale it up, right? And we can't have it starting at 0. It wouldn't fit on the graph. We probably wouldn't even see it. So we need to make sure it starts at that lowest temperature when we scale it up, after we scaled it. And so this is what our temperature will then depend on, instead of using what we have here for our lid space. So let's put that in, right? So for x, right, we'll just find x values. Temperature will be the critical temperature of our compound, which has been water, minus, I put plus there, it's supposed to be minus, my bad, minus, right? Minus 275 times negative NP, not exponential, right? Negative x plus 1. And that we need to scale, make sure it starts in the correct spot. And remember, these x's is in terms of exponentials. So 0, so it starts at 1, or well, starts at our base value, right? And how close do we want it to get to our limit value? Well, 7 is a pretty good value, and we want a bunch of points to make it as smooth as possible. I forgot to multiply. All right. And now we will see how this looks. And that looks pretty good, right? Really good. And that is how you graph the Maxwell construction for the SRK EOS in Python here. Thank you.